Okay, let's go ahead and start. Welcome everyone to Asteroid Day at CU Boulder. I'm Oscar Fuentes Munoz, a PhD student at the Aerospace Engineering Department, and your host. And today we're here to celebrate the International Asteroid Day, which is recognized by the United Nations. And today and throughout the week, you'll see hundreds of events going on. But what are we celebrating? Well, today is the anniversary of the Tunguska event, which was an explosion in the atmosphere caused by an asteroid in 1908 that just flattened a forest area the size of Boulder County. So like 80 million trees. And well, we have other examples of asteroid impacts like the Chelyabinsk meteor. We all remember from the news and all the videos online. But really, the difference between an asteroid impact and all the other natural disasters is that this one can be prevented. So Asteroid Day is dedicated to raise awareness about the risk of asteroids. But also, there's many reasons to learn and to study asteroids. The other bigger one is about the scientific relevance, because they are the remnants of the formation of the solar system. So they teach us a lot about our own origins, and we may also use them as resources in the exploration of the solar system. So for these reasons, we need to characterize their properties, their origin, their future, and we need to learn how to explore them, how to get there, and how to navigate around them, or even bring samples back to Earth. While doing so, we also want to involve our community in the scientific process, of course. And well, CU has a lot to say about that because they have been doing it for a while and involved in many missions. And here you can see just a few of the current ones. Now see OSIRIS-REx is bringing back home samples from asteroid Bennu. And in the future, Janus will visit 2 binary asteroids, and DART is going to demonstrate planetary defense technology, which, 40 years after the hypothesis that the dinosaurs were extinguished by an asteroid, humans are demonstrating this technology, which I think it's amazing. And well, for this, we organized this Researchpalooza, which is a session of short presentations from alumni, faculty, and students. Now we're about to start. It's going to be a good hour and a half. And for all the audience, if you have questions, please post them in the chat. And if we are well within schedule, we might answer some of them live too. And with that, I'll just give the stage to the first presenter, which is Professor Dan Scheeres, talking about Janus, a NASA SIMPLEx mission. So stop sharing.
Okay, thanks very much, Oscar, for taking the lead on organizing and scheduling and lining up speakers and all this for this event. It's very exciting. And thanks to everyone who's dropping on and presenting and just to check out what is going on at Colorado in terms of asteroid research. So I'm going to talk just a few minutes about a mission that we've been involved with called the Janus mission. It's a NASA SIMPLEx mission. Well, let's get going talking about it. So Janus is essentially going to send 2 small sat spacecraft. Each of those spacecraft will fly by a different binary asteroid. And as we fly by the binary asteroids, we'll take a series of visible and thermal infrared measurements of these systems in order to characterize them and better understand these particular bodies. And what I'm going to do is talk a little bit about the mission and the motivation and how we're going to carry this out. So here's sort of a org chart just showing you what's going on with the Janus mission. It's really a collaboration between the University of Colorado, it's where I am, and where the mission PI office and mission oversight occurs, Lockheed Martin, which is where project management and the spacecraft build and design and mission operations occurs, and Malin Space Sciences, who is delivering our instrument suite. We have a very small but focused science team, including people from across the US and also Petr Pravik from the Czech Academy of Sciences. I'm the PI, and Jay McMahon, who you'll hear later on today about some different missions, is the deputy PI. One more thing, we are a SIMPLEx mission, so that means that our total budget is quite constrained at less than 55 million. We also are a rideshare with the Psyche launch, which launches next August in 2022. So we're hot and heavy in the development of the spacecraft, about to enter ATLO, and we're on target so far. So let's look at the Janus mission in a nutshell. So we launch with Psyche. Our cruise is about 42 months. After launch, this is a Sun-Earth rotating frame. We go into a 1.5-year orbit, so that 3 years later, we come back, have another Earth flyby. That gives us a little gravity assist so that we can then send one spacecraft to 1991 VH, and this occurs anywhere between March and January of 2026, and the other one to 1996 FG3, and this occurs anywhere from March to April in 2026. The target binary asteroids that we have really make the mission. Each of these binary asteroids has been very well observed over the last few decades, which means that we have a lot of information, and we know their orbits very precisely, so we can do a very precise flyby and close flyby of these particular objects. They're also very interesting, and each one of them pose some fundamental questions that our science will actually study and help resolve. And even though we have shape models of these bodies, these shape models are only at the decameter scale of accuracy. And with our flyby, we'll be able to get down to meter scale of accuracy for these bodies. So when we get to the asteroids, what we have is essentially a simple flyby, and our flyby distance is on the order of 70 to 80 kilometers. As we go through the flyby with our small sat, we're actually able to pivot and track the asteroid throughout that flyby. So we'll actually take observations at this whole range of phase angles. And when we do that, we'll be capturing these pictures at different levels of resolution, with the highest resolution, again, giving us over 800 pixels across the body. We'll also be taking thermal IR observations throughout this period as well. And on approach and departure, we'll take photometry observations as well, which will help us really nail down the dynamics of this binary asteroid across this few day time period that this flyby will take. The instruments we fly have high heritage and proven performance. It's a visible imager that flew on OSIRIS-REx, and an infrared imager that's flown on numerous missions at the Earth. And these are provided by Malin Space Sciences, an excellent provider. And what is it that we're trying to understand with the Janus mission science? And in a nutshell, why should we be interested in studying binary asteroids? One reason is that they're ubiquitous in the asteroid population, consisting about 15% of all asteroids. We believe that they form when we have rubble pile asteroids that fission due to very high spin rates, and that these are one of several different pathways that small rubble pile asteroids travel down. Fundamentally, we think if we understand binary asteroids and how they're formed, we will get a lot of insight into just the geophysics of microgravity aggregates, which are really ubiquitous across the solar system and across time as well. So it also addresses some very fundamental physics questions that we'll be able to get to with our mission. We have two main goals with our mission. And I could actually talk for quite a while about all the different science that we're doing. But one of those goals is to understand how binary asteroids form. And essentially, the images that we'll take, thermal and visible, through the flybys will give us key information about the surface morphology of these bodies that will help us to sort of extract different and test different hypotheses for how binary asteroids are actually formed. This one movie just shows one formation mechanism that's hypothesized. There are several other ones as well. The other goal is to study unique aspects of each of our Janus targets. For 1996 FG3, this is a very primitive asteroid. It's also in a very stable state. And in fact, all the thermal forces acting on the asteroid are actually balanced by all the internal tidal forces that are acting on it as well. So by mapping this FG3 thermally, we'll actually get a lot of insight into tidal processes that are occurring within the components of this binary asteroid. The other asteroid, 1991 VH, is an S-type asteroid, and it's a bit unique in that it's in a highly excited state, as you see in the movie on the right, and it hasn't settled down into a stable equilibrium state. So with our flyby, we'll be taking key information and key data to really test and understand why it's stuck in this particular state. So that's a very brief high-level summary of the Janus mission. Just to give you the status of it, we are confirmed and we're currently in phase CD, and we are on budget and on schedule. All of the parts are starting to come into Lockheed Martin, and Atlo starts, which is basically bolting the whole spacecraft together, this August. And launch will be a year from this August. Janus, with our science, will provide the first high-resolution scientific observations of multiple NEO binary asteroid systems across a full range of phase angles. We'll also provide insight into the mechanics of rubble pile bodies and into microgravity geophysical processes in general. Janus is also exciting because it sort of defines a new spacecraft and mission profile for small sats that can provide a very responsive scientific and planetary defense capability for NEO characterization. And overall, we're very excited and ready and able to serve as one of the inaugural members of NASA's SIMPLEx program. So yeah, thanks a lot for your attention. And if there's a quick question, I don't know if there's time, but yeah, I'll give it back to you, Oscar.
Sure, thanks. There was a quick question, but Jay jumped in and answered it in the chat, so about the navigation for Janus provided by Lockheed Martin. So I'll just introduce the next speaker. That's Sorli, and the development of a thermophysical model for binary asteroid systems. So whenever you're ready.
Awesome. All right, thank you so much. So my name is Kaya, and I am a graduate student in APS working with Dr. Paul Hain at LASP. And today I'd like to talk to you about our work on thermophysical modeling of binary asteroid systems for the Janus mission, actually. So the timing of, or the layout of the talks worked out incredibly well because you just got that great talk from Dan. But Janus, I'm just going to reiterate those two target systems. Janus is visiting two different binary systems, and they have very different dynamics. So 1996 FG3 is believed to be a stable binary, whereas 1991 VH is potentially in a dynamically chaotic or unsettled state. So where does thermophysical modeling come into this? And as a matter of fact, it's kind of a crucial component to achieve several of the different mission science objectives for Janus. At a high level, these involve identifying and constraining models of binary asteroid formation, like Dan talked about, as well as looking at the dynamics of these systems. So we really want to measure the secondary Bjork coefficient, and I'll talk about that in a sec, for the stable system. And we also want to test why the unsettled system is unsettled. Why is it like this? More directly, one of the level 1 requirements for Janus is to use observations to constrain a thermophysical model of the secondaries, with greater than 15% accuracy and precision. So with that in mind, kind of our ultimate goal with a lot of this thermophysical modeling that I'll talk about is to estimate the secondary Bjork coefficient. And to look at dynamics and orbital evolution, you really want to understand potential perturbations. And Bjork is a very important one. So if we look at like this image down here, if you have incoming solar radiation that gets absorbed by an asteroid, it eventually has to get re-emitted. But because these asteroids are rotating, they're going to be re-radiated in a different direction, essentially. And if that re-radiation is asymmetric, say because the body is or for some other reason, that can induce a torque that alters the secondary's orbit. Though small in size, over a long time, that can actually lead to enormous effects, like breaking the binary apart, changing its spin, or even leading to a contact binary. So in order to estimate the size of this effect, we need to look at things like topography and shape and all sorts of different effects like thermophysical properties. But we also need surface temperatures over time. So that kind of leads me to the big questions that our work is trying to answer. So first of all, what are the surface temperatures of these asteroids and how do they change with time? And second, we want to use those temperatures to measure the magnitude of the Bjork effect and look into how it's influenced the dynamical evolution of these systems. So in order to go after the first one, our previous work thus far was actually to create a 3D model that could generate surface temperatures over the whole body. So we did this by coupling a highly validated 1D thermophysical model from Hain et al. 2017 to a 3D shape model provided by the Janus team to calculate per facet temperatures. And in addition to coupling the models, we also calculate solar fluxes. You can see them overlaid on the stable system's primary right here. And we feed fluxes along with compositional parameters to the model. We allow it to equilibrate for a long period of time. And then it gives us diurnal temperatures, so over the course of a day, if anyone's for the surface and near subsurface. So we've made this model, and we've also actually already done preliminary temperature modeling on all 4 Janus bodies. So I don't have time to go into all those results right now, but kind of here's an example of what we can get. So this is 1996 FG3 in the primary. We've done both primaries and both secondaries. But for a given thermal inertia range, you can get diurnal temperatures. That's what's overlaid right here on the shape model over the course of an asteroid day. And you can also get some really useful metrics like diurnal equatorial temperature amplitude. That's roughly how much it changes over the course of a day. Notice that as the thermal inertia goes up, you actually get a smaller range that is consistent with what we expect, since thermal inertia is kind of roughly resistance to changes in temperature. We can also get things like extreme values like maximum and minimums. So I can talk about those or send my presentation on that to anyone if they're interested in the specific temperatures. But that model that we've already made largely focuses on these red arrows. So this incoming solar radiation. What about the rest of these arrows? What about the reflection and the re-radiated heat and all that? Turns out, over long periods of time, that can actually have a big impact on surface temperatures and thus on that Bjork coefficient we're talking about. So how do we account for all that extra radiation bouncing around? And the answer largely lies in something called ray tracing, which if you've worked in animation or anything, you might have heard of. So ray tracing is essentially casting rays between 2 different points, in our case, facets on a shape model, to see what's visible to that facet. So basically, it can help you set up topography by saying this facet can see this facet, but it can't see this one. And it can also help you understand reflection. So if light comes here, where does it scatter? On a larger scale, for like the binary as a whole, it can help you understand radiation exchange between binary pairs or lack thereof in the form of eclipses. So we are doing several other improvements, but that's the most important one. And what that allows us to do is better representation of radiation in the system as a whole, which in turn allows us to satisfy that first question, which is improved surface temperatures. And all of that goes towards our ultimate goal of more accurate Bjork estimation. All right, that's all I got.
Awesome. Thank you, Gaia. It's very nice. Up next, we have Simon Tardivel with the regolith science of the MMX rover.
Hi, everyone. Can you see my screen now?
Yeah.
It's good. All right. I don't see the chat right now. Oops. All right. Open the chat. Okay. So thank you for inviting me for to give this talk. For people who do not know, CNES is actually in Toulouse. Most of the people at CNES work in Toulouse. It's the French space agency. I'm Simon Tarivel, and I was on a CU alumni. I worked with Dan, did my PhD from 2020 to 2014 on landing on asteroids. And today I'm going to talk about the regolith science of the MMX rover. And I will first start with addressing the elephant in the room, that is, should I even be talking at this conference? Because Phobos is not an asteroid, and most probably, we don't know, but most probably not. It's the largest moon of Mars. You can see it on the right. You see also the big sticky crater that is the most defining feature of Phobos. So Phobos has many different hypotheses for its formation, but we can say, I think, that definitely that it's a giant impact right now, because the asteroid capture and the co-formation are not really as easy as they were once thought. So Phobos does have many characteristics that make it close to an asteroid. In particular, the low gravity it has that makes it a small body. It also has a very similar spectrum to some asteroids, and it has a low density, somewhat close to Itokawa, for example, that makes it also probably a rubble pile. And so those aspects are aspects of asteroids. However, it has some big differences with asteroids, and the most notable one is probably that it doesn't have the same dynamical environment. When we see Dan talking about like equilibrium between the small asteroid and the big asteroid, the secondary and the primary, that doesn't happen with Phobos, because Phobos has Mars that is gigantic next to him. And so when Phobos orbits, everything that happens to Phobos is linked to its coupling with Mars, and Mars is a big planet, and so those are not the same dynamics we have. Also has probably some other features that I put question marks because not sure. It probably was more stable dynamical environment, probably had a smoother surface. We don't know at the fine scale, but probably has a finer terrain that you could find on Ryugu and Bennu, and it is probably an old surface, although the age of Phobos itself is a big question. So the JAXA mission is actually a sample return from Phobos. Let me open my other window that has closed. Thank you. It's a sample return from Phobos that will launch in 2024. So we'll have a Mars transfer that will start in September 2024 from Tanegashima. So this is the spacecraft leaving the Earth, going to Mars. You see here the spacecraft is in 3 parts. Of course, they're connected. The JAXA spacecraft has the propulsion module that's on the left, and there's the sample return module, and then the exploration module. And as soon as it arrives on Mars, it has to use all this propellant. So there's only the 2 other parts, the exploration module and the sample return module. During this observation from 2025 to 2027, he will do a characterization of Phobos, a mapping, most important, and of course, some landing site selection that allows us to know where we're going to land. Then we're going to have touchdowns in 2027. It will be first the rover that we'll talk about very soon, that will land in February 2027. Here it's a posture that the rover probably will never have, I hope. But yeah, it's how we say that, how we show that it's deployed on Phobos without any sort of gear to slow its descent or allow it to come to rest. Then we have a touchdown 1 and touchdown 2 of the main spacecraft of JAXA that occurs a few months later. Then there's again some Phobos and Mars observation. Then there's a flyby of Deimos, the other moon of Mars. And finally, there's a Earth transfer that starts in 2028 and ends up in 2029, again arriving in Woomera, Australia, just like Hayabusa 1 and 2 did in 2010 and recently 2020, if I'm not mistaken. Or 2019, I don't remember. Time flies. And finally, for the Earth transfer, of course, the exploration module is left in the Mars system, and only the sample return capsule comes back. So MMX, honestly, will be the first mission to not only attempt a sample return from Phobos, but from the Martian system, and that's pretty hard. That's pretty complicated if you consider that Mars is a really big gravitational well, and if you also consider that there's probably the regolith at the surface of Phobos is probably also made of a lot of Martian material. So maybe, and I think JAXA knows that, they will be the first one to sample Mars in a way by sampling Phobos. So let's talk now about the MX rover. So the rover, it's a scout, it's a demonstrator, and it's also an in situ science explorer. What it means is that we take risks before the mothership, we demonstrate our wheeled locomotion because we have wheels on a small body, and then we also do some regular science. But our primary objective, and that's very important to us, it's to de-risk the landing of MMX, and that is done through the characterization of the regolith behavior on Phobos. So from our inception, our rover has been about the observation of regolith through the regolith-wheel interaction, and that's why it has wheels. And it's also why it has wheel cams, so cameras that look at the wheels from within the rover, from within the chassis. It's 4 megapixels, it has a 100 microns resolution, so it's really, really a fine detail camera, and it takes movies while we're driving at low speed on Phobos because, of course, because of low gravity, we can't really drive very, very fast. If we take a zoom on what's inside the rover, you have the rover on the left. If we just remove the chassis, the wheels, everything, we look at what's inside, you can see the wheel cams. I can point that here. This wheel cam look at the front wheel, this wheel cam at the back look at the back wheel and the trench. And this is kind of the pictures we are having right now. The texture is all wrong, but this is what we will be looking at. And we hope to see regolith moving and have those gorgeous movies to look at to understand how regolith behaves in low gravity. So this is the science matrix we have of the of our MMX rover. I just show it here to insist on the fact that our experiment is really balanced in physical aspects of the regolith and, let's say, more traditional compositional aspect, what it is made of. We directly support the mission on many of its topics, which is the surface formation, process and evolution, the history of the geology there, some thermal properties too, composition, and we provide something that the spacecraft didn't really have before, although it lands, so it does have some of it. But it's ground truth for the orbital measurements that you do, because when you do orbital measurements, you already use a lot of models to infer what is the real thing you want to measure, and context for the sample collection, because we will be deployed at the landing site, so we'll be able to see what's around. And here, it's not CNES itself doing the effort on the science, it's our partner labs, and for the wheel cams, it's at Isaiah Sparrow with Naomi Murdoch, and for the nav cams, it's Pierre Van at the LAM. The nav cams look at the front of the rover. I'm going to hurry for the last 2 minutes explaining the wheel regolith interaction, what it is that really interests us. So today, Isaiah Sparrow and Naomi have been focused on the problem that is the direct problem. So how does regolith behave around a wheel in a given soil? But that's kind of the easy problem. It's pretty hard already, but it's the easy problem. The problem they have to tackle now is the inverse problem. What are the soil properties given the behavior around the wheel? Because we will see the wheel turning, we'll see regolith around it moving. And so what now are the properties of this regolith? So it's a pretty hard problem. And the way that they are tackling it right now is to go basically with all the tools we have at our disposal. So first, they have done a lot of work on Chrono. It's an open source DM software that Cecily Sunday, who was a JPL engineer before and now is doing a PhD at Isaiah Sparrow with CNES. She has developed a lot of modules in it to really be able to model regolith in low gravity, which is a different regime than on Earth, let's say. So we're doing some simulations. They also have built here, I take it from their presentation, a bench to study what's happening in 1G with a wheel, with the rover wheel, and in a camera pretty similar to our wheel cams. And of course, linking everything through theoretical analysis and trying to get some understanding through that. So this is what they're doing. Cecily is defending in October of this year. So she's publishing as many things as she can. She has like several papers coming out every month now, almost. It's hard to follow, but stay tuned for the results and publications because it's pretty cool. And I thank you for your attention.
Thank you very much. That was very interesting too. Yeah, I'll give up. I think we are on schedule. Maybe there's a short question. Otherwise, we'll just move on to Paolo.
Yeah, sure. Go ahead. We can move on. I can answer in the chat if something is needed.
Okay.
Thank you.
Sure. Thanks. All right. So up next we have Paolo Panicucci with simultaneous localization and mapping for asteroid approach.
Hi, can you see my screen and hear me?
Yes.
So, okay, the hand, okay. Hi everyone, I'm Paolo, postdoctoral fellow at Politecnico di Milano, and I was visiting a PhD research at Orca Lab at Jay's lab during spring 2019, and I'm here to present this work I did during my PhD about simultaneous localization and mapping for asteroid approach. This is the plan of the presentation. I will introduce the motivation, motivation, and then the proposed methodology with numerical results, and then some conclusion. So here I put an illustration not to scale of all the visiting asteroid that we visited in the last decade. What's important to see is the fact that asteroid properties are generally heterogeneous, which means that they cannot be known before the approach, before the arrival, which implies that we need to estimate them during the navigation process within the navigation process itself. But how do we navigate around asteroid nowadays? As you probably know, the navigation is based on the deep space network tracking with some optical navigation and shape reconstruction done thanks to the stereophotoglynometry. And then those two measurements are fused in a filter in order to compute the orbit determination solution. Unfortunately, this technique has several drawbacks, in particular because the deep space network operations are costly and delayed, and the stereophotoglynometry is not suited for onboard application, both because it requires human in the loop to check the solution, but also because it's computationally expensive given the high number of images required for this technique, which implies that autonomy is one envisaged solution to reduce mission cost, as also the deep space network utilization. And this motivates our studies about asteroid shape reconstruction and probe localization without the support of the deep space network. We concentrated in the asteroid phase, where the spacecraft is orbiting around the sun and approaching the asteroid. And the asteroid, which is rotating around its rotation axis here, which is inertially fixed, is resolved for the first time as an extended body. And the estimation goal are not only the asteroid rotational state and definition of the asteroid fixed reference frame, but also the asteroid shape and determination of the position and orientation that we will call in the future pose with respect to the asteroid fixed reference shape. The methodology, I will now talk a little bit about the methodology that we used to tackle this problem. In particular, by using, we have thought about using approach images to extract available information on those images, in particular feature such as here in the bottom part or silhouette in the top part. And thanks to those information, we want to determine the asteroid shape and also the localization with respect to this rotating asteroid. But unfortunately, it is a very complex problem because the localization should be computed with respect to an unknown asteroid shape. And also the asteroid shape should be reconstructed with an unknown localization, which leads us to a very known problem in the robotic community, which is simultaneous localization and mapping. The way we tackle this problem is the following. Let's consider that we have an asteroid. We have the first frame, the first camera, which is observing some landmark on the surface of the asteroid. And then we can extract a feature from the images. And then we continue, thanks to our tracker, to track and detect new frames, new feature in different frame, until we arrive to, after one rotational period, to a moment where you're observing the same face of the asteroid. So we can perform what is called in the SLAM literature loop closure, and we have thought, as we are observing the same phase, to track points from the last frame to the first frame in order to recognize this loop closure. Let's imagine here that frame number 5 is performing loop closure with frame number 1. So we can recognize that in reality landmark number 6 is landmark number 1. Which leads to the fact that we can recognize that loop and we develop a method to perform loop closure between frame 1 and frame 5, recognizing that landmark number 6 is in reality landmark number 1. And so then when this is done, we optimize the full interconnected graph that we created here in order to reduce the overall error in the SLAM solution. Once we have done this, we have thought how we can use the silhouette in this framework. We have thought about merging the silhouette information with the optimized SLAM with some to enhance the shape reconstruction of the asteroid. In particular, one, this is the SLAM solution is found. We can use the asteroid fixed position and orientation to go to in a shadow robust silhouette reconstruction in order to compute both both the silhouette, which are robust with respect to the shadow, but also some silhouette-based reconstruction point. The silhouette are then used to filter some landmarks, and those landmarks here we use this filtering mainly because the landmark can go outside of the body, and as this landmark going outside the body, and the silhouette are sharp boundaries of the body itself. We want to discard the landmark that went out of the body as we are observing it in the images. So we filter the landmark and we fuse those landmarks with the silhouette-based reconstruction point in order to compute a polyhedron. This was the methodology. I will enter now in some numerical results we developed with the software from Airbus Defense Space at ISAE Super-O. And so we are considering an Hayabusa-like spacecraft approaching the Itokawa asteroid, which is rotating around its rotation axis. So you have here the geometry of the approach. We can track during 12 hours, so one rotational period, different type of feature on the surface of the asteroid, and we are observing the asteroid from 9 kilometers, more or less. Those are the results that we are obtaining from the position and orientation. In particular, we have a 50-meter accuracy for the position, for the true position error, and which is a very nice estimate if we consider that we are observing the asteroid from 9 kilometers. And here you have the MRT, which is a representation of the orientation, the MRP error. You can, in order to have an order of magnitude, 10 minus 3 MRP error, it's about 0.2 degree. And also in this case, we are very accurate in our orientation estimation, which is mainly due as we have this sinusoidal trend to the error we are obtaining in the rotation axis here, which is about 0.2 degree. Then we can extract shadow robust silhouette, as here in the animation on the left. We are compensating the self-shadowing effect given from the bad illumination angle of Itokawa, but we are also discarding some concavities here in the bottom half of Itokawa, which give us some artifact in the reconstruction, such as you can see here in this animation on the right, for the south pole of Itokawa. The volumetric error, it's about 9% with respect to the reference shape, mainly due to these artifacts, but the local reconstruction error mean, it's about 2.7%, which means that our reconstruction is quite good. Finally, we try to evaluate visually our reconstruction. In particular, here on the left, we have the images that we gave to our algorithm as input in order to compute the SLAM solution. And here on the left, we are simulating some synthetic images with the position and orientation for the spacecraft as estimated from the SLAM solution. And then we're using also the asteroid shape reconstructed in order to simulate those images. The fact that two of them quite agree gave us quite confident that the reconstruction is well performed in general. To conclude, in this study, during this study, we performed as SLAM estimation, thanks to a SLAM algorithm that not only reconstruct the asteroid shape, but also estimate the asteroid fixed reference frame, the asteroid fixed rotational state, and reconstruct the spacecraft position and orientation with respect to the asteroid. And then we enhanced the reconstruction thanks to a silhouette-based reconstruction algorithm that we developed, which is very robust to shadows in general. And future work that we are trying to put in place right now is to merge the presented algorithm in a larger PFP GNC pipeline in order to perform also something such as delta V ranging. This is intensively studied at CU Boulder, and also study the embeddability of the proposed algorithm and the applicability of the estimated reconstructed shape for model-based tracking techniques such as the algorithm that you see here on the left. Thank you very much for your attention. I will be happy to take any question if there are any. And if not, we can chat it offline or you can contact me at my email address. Thank you very much.
Thank you very much, Paolo. And yeah, I will encourage everyone to keep on doing the interesting discussion on the chat. And for the presenters, even if we start to run a few minutes late in the schedule, you can just keep your duration of your talk. That's fine. So next, we have Jacopo Villa with gravity estimation at small bodies using hopping artificial probes. whenever you're ready, Jacopo, you can.
Yeah, sorry, my bar to share has disappeared.
Move down, it should reappear. Move to the side of the screen.
Yeah, I tried, but it doesn't. Okay, I have to log off. I'm so sorry. I'll try to relog.
Okay, you can continue, or I can stop your sharing. Maybe you can try now again.
Okay, thanks. Let's try again.
Otherwise, we could see the slides too that way, so that can work too.
Yeah. Okay, can you see the slides now?
Yes.
Yeah, I'll probably just stick to this. Sorry about this. Okay, so my presentation is about gravity estimation at small bodies using hopping artificial probes. And this idea comes from a NASA innovative advanced concept that was led by JPL and has the name of gravity poppers. So when it comes to, okay, now, yeah, I need to skip the hidden slides. So let's see if, okay, now it should work. Okay, can you see it correctly now?
Now it works.
Okay, thanks. And sorry again. Okay, yeah, when it comes to planetary interior and mapping planetary interior, there are mostly three techniques that are used in the state-of-the-art: ground planetary radars, seismology, and gravity science. And all these techniques are complementary, but when it comes to applying them to small bodies, they encounter challenges. Having said that, which we discuss in the next slides, gravity science is what gravity poppers focuses on. So what is gravity science? Gravity science is measuring and estimating gravity field of a planetary body or a small body. And by doing so, we can infer its interior structure and so the mass distribution. Usually this is done by tracking the motion of a spacecraft and by looking at the gravity anomalies that a spacecraft encounters and observes in its motion around the body itself. Here's an example on an illustration for the Grail mission, where two spacecrafts were used to recover the gravity anomalies of the moon. So when it comes to small bodies, it's a bit different from bigger bodies such as the moon and Mars. If you look at the bottom heat maps here, we're seeing the spatial resolution of the gravity, of the observed gravity. And when it comes to moon or Mars, we can get a really high spatial resolution. But when it comes to smaller bodies such as Scheeres or Titan and Enceladus, it's more tricky to have a high fidelity gravity reconstruction. And this comes down to, well, the bodies are smaller and so weaker gravity. But the three key points are that we lack more precise OD measurements, we would need lower altitude orbits, and we would also need a higher coverage of the surface, so a higher spatial distribution. So the gravity poppers idea is trying to tackle all the three of them. And so the mission concept is that we have a mother spacecraft deploying a swarm of probes, artificial probes, that are able to repeatedly hop from the surface in a suborbital motion and a kind of random motion hopping from the surface. And the mothership is able to track these probes with, for example, optical tracking, and by reconstructing their trajectory is able to estimate the gravity field of the central body. So here's a quick animation to show how the concept works. So we're deploying the probes from a mothership. This is the mothership's view. And you can see all the trajectories starting this that resembles a chaotic motion around the body. And it's really important to recover with high precision all these trajectories to get the gravity field of the body itself. So the first step is to track the probes, as said. And we mostly focused on optical tracking because we realized it's leading to really good performance in and of itself. And we looked at two probe designs or two tracking strategies, which are really bound with probe design itself. So on the left-hand side, we have like passive reflecting probes, usually just white-coated probes that span in the order of 10 centimeters or more. As you can see by this plot, we can see that even with 10 centimeter probes or 15 centimeter, we can get a reasonable SNR to observe the probes on the surface in front of the small body, as it's shown in this simulated image on the top. The other approach, the other design is LED strobing. In this case, we would focus on strobing an LED for a specific band that then can be filtered with a bandpass filter. And even in this case, we can have higher observability. And this is actually even better because we could have smaller probes and suffer less from non-gravitational perturbations. In terms of gravity results for this concept, we were surprised to see that it outperforms the state of the art of at least one order of magnitude. We're comparing here in the right plot with the OSIRIS-REx case. As some of you may know, they tracked the mission tracked particles, natural particles around the body. And here's a spectrum of the degrees of the gravity field SNR that could be observed. And as you can see, OSIRIS-REx was able to track in the order of hundreds of SNR for the lower order gravity field, whereas the gravity poppers concept is able to get at least one order of magnitude better under current assumptions. So we try to resemble the OSIRIS-REx mission to recover a similar setup. And this is to give an idea of the spatial resolution that we would achieve with such a high fidelity gravity field on the surface of Bennu. Just to show very quickly the probe design here, if we have an LED strobing, we would need, of course, some power and some hopping mechanism, which interestingly was already tested in a micro-G or in in a micro-G environment. And you can see that even a simple hopping mechanism is able to hop off from the regolith-like surface, which is interesting for this application. This is what the entire spacecraft would look like. So we would have the probe stored in a canister and an observing camera. And then finally, the applications of this entire concept can span in a variety of small bodies and can be used both to estimate morphological features such as boulders or subsurface voids, but also to measure the time-varying gravity field, which is typical, for example, of comets or some other active small bodies. Yeah, that's all I have, and I'm happy to take any questions offline or anything else.
Very cool.
Thank you, Jacopo.
Again, you need to stop me sharing because I missed the bar.
No problem.
Thanks.
That's it. So I'll refer questions to the chat, and we can continue with Duncan's talk about 60 years of high school students and asteroids.
Okay. Screen visible? Okay, and sound. So 1957, Sputnik was launched, and all of a sudden, we were in a space race, and we were not ahead. So at that point, the headmaster of the oldest private school in California, called the Thatcher School, wanted to help. And so he came up with the following idea. We really need to convince the top high school students to go into careers in science. How can we do this? And he contacted Caltech and Stanford and Pomona, a bunch of colleges, and they brainstormed and they said, well, if we could bring students together in the summertime, we could let them actually be scientists and see what it's like and get them all excited to do this as a career. And there was nothing like this ever before, so they just called it the Summer Science Program. Then they tried to dream up what should the students do to learn both theoretical and laboratory skills in science. And what they decided, let's give them all asteroids. So they broke the students into 12 teams of 3, and they said, you have one question to answer by the end of 6 weeks. We want you to find your asteroid and determine its orbital elements. Well, that of course is a challenge, because what do you need to know to figure something like this out? Run a telescope, learn coordinate systems, learn how to take, in those days, photographic plates, how to find an asteroid using a sky survey and your own images. How can you measure positions to an accuracy of microns? You need to know calculus up through vector calculus in order to understand equations of motion. You'll need to know spherical trigonometry because the sky is a sphere. And eventually you learn the whole orbit determination as Laplace and Gauss first worked out. Wow, that's a lot to learn in 6 weeks. So how do they do it? They have 5 hours of lecture a day. They have 4 to 5 hours of homework. Their teams split time on the telescope. So they work really, really hard. They get a break twice a week. A guest lecture is their break. That's Richard Feynman, who spoke 8 summers to the group. Eric Cornell, another Nobel Prize winner, speaks every summer. Martin Schmidt on the right, who discovered quasars, spoke to the group for 32 consecutive summers. He loved talking to these students. So excited we got him to play volleyball. Nowadays, the program is still running after 63 years. The imaging is digital, but it's the same challenge the students are given. Oh, near Earth asteroids, because we can go fainter. That's what they study. They still got to get the orbit. So what's been the result of this? It has been successful beyond all expectations. It transforms these high school students because for the first time, they have a peer group. They have people they can talk to who understand them, they can work with. And they're pushed to work much harder than they have, but they learn how much they can accomplish. They learn what to do when they don't understand something, which is pretty novel. If you're the smart kid in the class and you're used to that, you have to deal with, oh my God, I don't understand. Oh my God, I'm not the first kid in the class. And they learn that's okay because they have these wonderful supportive peers and staff, no grades or anything. You're just doing science for its own sake. So they learn how to work in teams and their career aspirations are greatly enhanced. I love this quote from one student. She said on the very first day, I found my planet. So a majority of the students are inspired and 2/3 of all of them go to MIT, Caltech, Ivy League, or Stanford. And they are so thankful for this experience, they donate to the summer science program every year. That's why it's still going after 63 years. Yeah, one of the students invented the spreadsheet and made $100 million. They do really interesting things after they go to college and graduate. Nowadays, unlike the early days, half the students are female, 15% are minority. So this summer science program is actually expanding. We have enough donations to open a new campus, and we are recruiting faculty and TAs. And so if anybody is inspired by this kind of a thing, it's really amazing to teach 36 students like this. They're so enthusiastic, so filled with questions. It's very different from teaching at a university. I was a student here. That's why I talk about it. I went back 3 summers to teach. One of my students became the physics chair at MIT. That's Ed Bertschinger. Some of you may know him. My student Scott is executive director of the National Space Council. Anyway, it's a fun thing to do, and I am recruiting. I do have a little video. I was going to play just the first 4 minutes that also give you an idea of what this program is like. And if anybody is motivated to find out more, go into chat and I'll correspond.
The summer science program stands alone in the world. 50 summers of challenge and intellectual excitement, and today, stronger than ever. How did this happen? And why has SSP thrived? Let's go back to the beginning. In a real sense, SSP was conceived on October 4th, 1957, when the Soviet Union launched Sputnik.
We can't see the video. Sputnik represented a shock that we had fallen behind technologically our adversary in this long-term struggle.
Can you just hear the sound?
Yes, that's correct.
I see why. Here it comes.
Okay. Scientists and give them a summer that will multiply their choices and change their lives. With support from Caltech, Pomona College, Harvey Mudd College, Hughes Aircraft, and several foundations, the summer science program started up in 1959 with 26 boys from 4 Southern California counties.
The primary goal that we have, and the design of the program is built around, is the intellectual and social development of the students. That is what we're here for. And we use the math and science to accomplish that goal.
In 1959, with the space race fully engaged, SSP's founders made the obvious choice for the summer curriculum: astronomy.
Well, if there's a magical ingredient in the summer science program, I think it's in this asteroid problem. This is a problem that has a beginning, a middle, and an end. Most problems don't. It was clear to me from the beginning that the curriculum laid down by the Hughes Aircraft Company would never work. So I turned the thing around more or less by insisting that the kids take photographs of the asteroids first, measure their position, then determine the orbital elements.
Astronomy turned out to be an excellent long-term choice for 3 reasons. First, it requires a lot of sophisticated math and physics. Second, it's rarely studied in any formal manner in high school, so all participants arrive with the same general levels of knowledge and interest. SSP's founders knew this. What they didn't realize, and what turned out to be a huge plus for teenagers, is that when you do astronomy, you get to stay up really late at night.
You may think that math and science doesn't have much romance, magic, or wonder to it. For me, it was an eye-opening experience because when I came here, I was doing math and calculus and writing programs, and to think that all these numbers on a piece of paper could describe the motion, the changing velocity, and everything else. I mean, if that's not magic, I don't know what is.
We had some problems with our plates, and I don't really remember what the problems were, but I remember it wasn't looking good for us to get our orbit.
We had all our coordinates, and we had a nice series starting up here, winding up down here. There was this one point out in the middle of nowhere.
I know, look. All these were bad.
And we went back and looked at the plate and realized that what we'd measured was a little flaw in the plate. Something in the glass, whatever. That was no asteroid. It wasn't there on the star charts. That's why we thought it was the asteroid. But it was nowhere near where our asteroid was. We went back, we compared to the star charts, we found where our asteroid really was, we remeasured everything. The new point was exactly in the right place on the curve. But we'd only been dealing with these numbers. We'd never visualized what the data was telling us, or would have known right away that we were measuring garbage.
So that's basically it. That is the summer science program. It has a campus at CU Boulder, and it's going to be opening a new campus in 2022. And we are looking for graduate student TAs and faculty. So you can get me in the contact window should you be interested. Thanks.
Sure. Thank you, Doug. That was very nice. I hope you recruit a lot of people. And yeah, let's move on to the next talk. We have Spencer Boone with methods for autonomous spacecraft guidance around small bodies.
Okay, 1 second.
Sure.
Can everyone hear me?
Yes, we can hear you.
Okay. So thanks, Oscar. My name is Spencer Boone. I'll be talking about some spacecraft guidance methods that can be used around small bodies to hopefully increase autonomy, and I'll also be covering some work done by Don Kettle and Ken Noguri. And we're all PhD students at CU Boulder. Actually, Ken just graduated. And we're all in Jay McMahon's Orca Lab. And so I'm sure from the previous presentations you've seen that asteroids have present a unique challenge, and there's an interesting dynamical environment. So you have a low surface gravity, which is an interesting challenge in and of itself, and the non-spherical shape. And then any perturbations that would be somewhat negligible or a lot smaller than gravity around Earth become very large when we're orbiting around an asteroid. And what this means is that accurate spacecraft guidance around asteroids is a complex and time-consuming task. And currently for many, I won't say most, but many asteroid orbiting missions, maneuvers are almost exclusively planned on the ground. And there's a significant human in the loop component. And often this means that there's sort of off nominal hours work might have to plan a maneuver over Christmas or New Year's. And there's also a communications delay for missions that are far from Earth in deep space missions. And as Paolo mentioned earlier, it's for deep space missions, communications can be quite expensive if we're doing it from Earth. And so at the Orca Lab, we're developing a variety of algorithms that will help enable spacecraft to autonomously plan efficient and safe maneuvers. And hopefully we will have fewer people working over the holidays in the future. That's one of the objectives, but also, a lot of objectives in increasing this autonomy. And I'll start by talking about some work that Don Kettle in our lab has done. And so he's been looking at developing methods for using low thrust propulsion around asteroids, or electric propulsion. And so this type of propulsion has a much smaller thrust level than traditional propulsion methods, but because the asteroid environment has such small gravitational forces, it's particularly well suited for this environment. And it can lead to missions requiring significantly less fuel or propellant mass. And so Don has developed an algorithm that can autonomously plan and execute maneuvers around small bodies. And so you can see on the left here, this would be if it was an impulsive or very high thrust maneuver, but using Don's algorithm, we're able to execute the same type of transfer using a low thrust propulsion system and significantly less fuel. And this is the mission plan that Don recently generated, which I thought was very cool. And so he's using his algorithm, he's able to plan this very complex scenario that goes between several orbits and rendezvous at several points, and then adding in dynamic uncertainties and errors in the dynamics to the model. If you look on the right, Don's algorithm is still able to execute the mission plan. And so the next thing I'll talk about, unfortunately, I don't have much time to talk about each one, but it's all very cool. And so you should reach out to either Don or Ken if you're interested in these. But the next one I'll talk about is some of Ken's work, and he's been looking at guidance under uncertainty. And so the environment around an asteroid can have a significant amount of uncertainty. There's uncertainty in our shape model, as we've seen in several presentations. There's uncertainty in the levels of solar radiation pressure. There's uncertainty in our navigation solution, and then errors in how our maneuvers are executed. And so how do we ensure that the guidance scheme can account for these uncertainties in a robust way? And the answer is to use Ken stuff, but I'll give a brief overview of how it works. And so if you imagine Ken ran a simulation for this very interesting orbit, which is called a resonant terminator orbit. And it's a periodic orbit, but it's able to get full global mapping of the surface of an asteroid. So it's potentially useful for science purposes. But if we add in uncertainties to this orbit and run our spacecraft through the dynamics without any guidance, we lose this periodic nature of the orbit. However, using Ken's stochastic guidance, if we apply that, we're able to maintain this periodic nature of the orbit and successfully achieve our global mapping in a robust way. And the last thing I'll talk about is some work that I've been doing. So a useful algorithm for designing continuous thrust or low thrust trajectories, but with longer thrust periods than what Don has been looking at, is differential dynamic programming. And so variations of this algorithm have been used to design the trajectory for Don, which visited Vesta and Scheeres, and for Psyche as well. And in this image, this is Psyche going from a wider orbit around the asteroid Psyche to a closer and more narrow orbit over many revolutions. However, this algorithm can be quite expensive to run. And so if we wanted to replan this type of trajectory, it would currently have to be done on the ground, and it would be a time-consuming affair. And so what I've been looking at is using what we call STT-DDP, so expand the nominal trajectory as a function of its higher order derivative, which can be called state transition tensors or STTs. Then we can use these STTs to run an analytical DDP algorithm, which can rapidly recompute near optimal trajectories in the vicinity of the reference. And then the computational time for this is reduced to seconds versus tens of minutes if we're using the standard numerical integration techniques. And so hopefully that gives you just a little taste of what we've been working on in the Orca lab. If you have any questions, let me know. There's always lots of cool stuff going on. Thanks.
Thank you. Yeah, it was nice to see all these different options. Let's move to the next presentation from Dan Luby about the Bennu shape model validation methods and results.
All right, can you hear and see my screen?
Yeah.
Okay. Thanks a lot. So my name's Dan Luby. I'm a spacecraft navigator at JPL in the outer.
I think we lost Dan. Does anyone else?
Yeah.
Okay. Okay, why don't we move on to the next presentation for now, unless we can get him back soon. Okay, which is unfortunate, but hopefully we can have him back and get him to present by the end of the session. And we'll move on to the next presentation, which is actually my presentation. So I'll just go ahead and share my screen. I swear I did not plan this to go ahead and present. Okay. Come back. Okay, there we go. So I'll present about the long-term dynamics of NEOs using semi-analytical propagation, a grad student at Professor Scheeres' lab. And yeah, we want to know the origin and the future of asteroids in the timescales of thousands and millions of years to understand what's their origin, but also in the future, whether or not they're going to be hazardous to Earth and what's the end of their lifetimes if they collide with planets, with the sun, or they exit the solar system. And well, there we go. And a subset of NEOs that's of interest are the potentially hazardous asteroids. In order for an asteroid to be cataloged as potentially hazardous, it requires two conditions. The first one is on the size of the object. It has to be larger than this threshold. It's, in my opinion, a little bit big because, well, the Chelyabinsk and the Tunguska don't fall into this category and they cause some significant damage. But anyway, the other condition is on the MOID, the minimum distance between the orbits of both the asteroid and the planet and Earth, which has to be smaller than these 0.05 AUs. And you can see the distribution of these objects. And one of the things that we want to understand is how this MOID evolves over time and the orbit in general. So for this, we're working on this semi-analytical propagation, in which we perturb analytically the object until it finds a planet. And this analytical propagation is done with accounting for the secular perturbation of the solar system. And then when we find an encounter, we evaluate this encounter numerically. And there's several applications for this, from just obtaining statistics of what's the outcome of what's the future evolution of objects, but also predicting of how often we will see certain events, like close encounters or collisions. And just to give some examples of the different dynamical environments, we have here 3 cases in which you'll see the different encounters that we found as the dots with the distance of close approach, and then the line around these points is the MOID, because it bounds what's the closest encounter that can happen. Of course, these encounters can modify the MOID, so then you see like these discontinuities in the propagation. And yeah, so here you can see, for example, in case 1, if the orbit is close to the orbit of Earth, then you see only encounters with the orbit of Earth and continuously. But if you have, for example, large inclination, then the periods of time in which encounters are possible can have these jumps that can be of tens of thousands of years, in which if you have a good analytical representation of the dynamics, then you can just jump and go to a faster propagation. And on the other hand, well, if you have large eccentricity and lower inclination, you can see that encounters are very frequent. And well, with this, we can compute probabilities of certain encounters and study the hazardous nature by the orbit. And yeah, we can do this propagation fast. And next, we're interested into seeing what's the influence on other parameters of the asteroids, like the physical properties that can be affected during flybys, as well, Alex will tell us later about the binaries, but also the spin rotation and the modification of the surface properties, which I'm very excited to get to. So yeah, with that, I'll finish my presentation. And if you have any questions, please have them in the chat and I'll be able to answer them later. And I don't know if we had any, okay, yeah, we don't have news from Dan. Hope he can come back soon and we'll have his presentation last. And I'll just let go to Alex, the next presentation.
All right, great, thanks, Oscar. So we started with binary asteroids. I'm going to bring us back, and we're going to finish with binary asteroids. And so I'm looking at how a close planetary encounter can change the dynamics of a binary system, with the main question being, can we turn a relaxed binary system chaotic? And so this is dominated by the spherical restricted full 3-body problem, where we have 2 arbitrary asteroids and then a perturbing spherical planet that's much larger and much further away from these other bodies. And in the full 3-body problem, we have to account for the forces between all these bodies and also the gravitational torques, because the dynamics are coupled pretty strongly in binary systems. So we can write out these equations of motion that are really complicated, and then we turn to numeric methods, the generally used binary asteroid simulator, where we can take as input a binary asteroid model and some initial conditions, and then also we add in our 3rd-body perturbations, and then GUBAS, the simulator, integrates these equations of motion, and we get out, the position, velocity, and the attitude of our binary asteroid system. So we approach this problem by first generating random hyperbolic trajectories. So we choose the hyperbolic speed and the closest approach distance of the flyby. So that's Q and V infinity. And then we randomly orient that in space by taking Monte Carlo draws of the longitude of ascending node, argument of periapsis, and inclination. So we generate 100 randomly oriented trajectories for these simulations. And then over time, we track the mutual orbit, semi-major axis, eccentricity, and inclination, along with the orientation of the secondary through Euler angles, the roll, pitch, and the libration. So once we do that, here's an example of the result of one flyby at 50,000 kilometer closest approach distance, where we're tracking all of our orbit elements and then the orientation of the secondary. So we can take an average change for each of these before and after the flyby, as well as perturbations to the orientation. And so then again, we repeat that 100 times for each trajectory. And so we can end up with 100 average results here. So here's semi-major axis, esoteric inclination, and then also the theta 3 in-plane libration. So as we'd expect, the further apart you get, the less perturbed the system is, and also the faster, in general, the faster the flyby, the less effect on the binary system we get. And so here we can compare with analytic models modeling the flyby as an impulse. So these green curves are the analytic approximations, and then the data points are our numeric solutions. And if you notice, the scales are logarithmic, so it looks like they're diverging, but they actually stay in pretty close agreement within about an order of magnitude for all of these test cases. Then we can look at disruptions. If the binary system breaks apart, essentially the secondary escapes from the orbit, or the two bodies crash together. And so these are just the percent of simulations that are disrupted. And as we get faster flybys, again, there's less time for the systems to interact, so we end up with fewer disruptions at faster flyby speeds. And then the last thing that's really interesting here is the loss of lock. What sort of flyby is going to cause the secondary to break out of a tidally locked configuration and start kind of an asynchronous rotation? So we define the flyby parameter, which includes the closest approach and velocity of the flyby, as well as binary asteroid mass, separation, and the mass of the planet. So sort of everything interesting in the flyby packed into one parameter. And then we can plot the average change in libration angle and then the maximum change that we see as a function of that flyby parameter. And we get really nice curves as a function of that flyby parameter. And we look at the analytic, there's an analytic prediction that gives us a sufficient condition for circulation, and that's at a parameter of about 0.07, which is this vertical dashed line. And we can see, well, on average, we'll start circulating after that. We do see circulation does start right around there. And so that's really cool that we can get a good prediction of when we'll lose this synchronous orientation. So that's all I have. I'm happy to take questions in the chat, or feel free to email me also. Thanks.
Mm-hmm. Thank you, Alex. Yeah, we're going up to the next, to the last planned presentation, if we don't get Dan back. This is from Jay McMahon. CU on DART, NASA's Planetary Defense Mission.
Okay, I don't see Dan back on here, so I'll go ahead, I guess.
Sure.
Let's see. Do you see the slides okay?
Yes.
All right, great. So I'm Jay McMahon. I'm a assistant professor in the SMED Aerospace Engineering Sciences Department here at CU. And as well as bookending this between having the two CU faculty members talking, I guess we'll also talk about some different missions that we're participating in. So first, this is just to show the wide variety of partners that are involved in this mission, and most importantly, to see that CU is, of course, right in the middle of everything, as expected. But this mission is being, or the spacecraft for DART is being built by Johns Hopkins by APL and being operated there. And of course, we have lots of partners, a lot of CU connections, which we'll talk about too. So here's a little animation that the team put together, which just gets you excited about what's going on. So here you see the DART spacecraft coming in towards Dimorphos, the secondary asteroid. Boom. Okay. So that's, in the nutshell, that's the mission. Right? We want to fly the spacecraft into the secondary asteroid of this binary asteroid system. It's the Didymos system. The primary asteroid is called Didymos. The secondary asteroid is called Dimorphos. And I'll show you another plot here in a minute just to look at the size, but a few things to pull off of here. So Didymos, the primary, is kind of Bennu-esque in shape, or Ryugu-esque. It's kind of that top shape that we've seen in a number of places, and it rotates quite quickly, 2.26 hours for the rotation. So that's the length of a day. The two bodies are a little over 1 kilometer apart from center to center. And then Dimorphos itself is on the order of 160 meters, and it's tidally locked as far as we can tell. So, which means that the same side is basically always pointing at the primary, and the secondary Dimorphos spins around its axis once per orbit. So it's always kind of going around, kind of like Earth's moon. So you can see there are 2 spacecraft actually involved in this. There's the DART spacecraft, which is the primary spacecraft, which will come and actually do the impact. And just before the impact, it'll drop off the Licia cube, which is being provided by our Italian partners. And that will image the impact and send back movies and things of the impact itself, and then the system after the impact. Okay, so here's the scale plot that I had promised. So just to give you some context, this is a nice graphic that the team put together. So here's Didymos, which is twice the size of the Eiffel Tower. Dimorphos is down here, and then the DART spacecraft, of course, is kind of a typical sized spacecraft, similar to OSIRIS-REx or something like that. A bit smaller than OSIRIS-REx, actually, but similar scale. So DART is a little bit of a different mission. Instead of being a science mission, this is really this is a planetary defense mission, and it's really more of a tech demonstration mission than a science mission. So there's 4 main goals involved, kind of level 1 requirements, so to speak, for the DART mission. So the first, of course, is to impact Dimorphos, the secondary asteroid of the binary system. I'll talk about the timeline in a little bit. The second is to change the binary orbital period. So we're testing this kinetic deflection opportunity on a binary system because it's much easier to change this binary orbit than it is, and to measure that change, than it is to change an asteroid's orbit around the sun. So this is a nice test to be able to do this. The requirement is to cause a greater than 73-second change on that orbital period. Remember, it was about a 12-hour orbit. So we've determined that if we can make that type of change, we should be able to measure the period change to within 7.3 seconds, or 1 part in 10 of the nominal value. And that's using ground-based observations. And then the 4th requirement is to measure the beta factor, which is this momentum enhancement factor. I'll show you a little more about that in a minute. So here's another sketch of what will happen to the orbit. So you can see this DART spacecraft is coming in. It's actually planning to hit Dimorphos head on. So they'll be coming towards each other. When it hits that Dimorphos, the delta V basically will be in its anti-velocity direction. So it'll decrease the size of the orbit, changing the orbit period by about 1%. Okay, so that's what we'll be hoping to observe them from the Earth. So here's a little chart talking about the beta factor. So this momentum enhancement factor, if it's 1, there's no enhancement. So the change in momentum of the asteroid from a kinetic deflection is just the asteroid absorbing the momentum of the spacecraft that hits it. Okay, so it's just an inelastic collision, the 2 things hitting together. Okay, if beta equals 2, there's some ejecta that comes out, which increases how much momentum. So there's the momentum transfer from the spacecraft hitting Dimorphos, and then there's extra momentum basically come from a kind of rocket effect almost of mass being thrown off. And as beta goes up, that increases. Okay, so if beta equals 4, we would get an even bigger impulse than expected. And it's very complicated modeling beta and trying to understand that, so we don't really know what it will be. There are, of course, predictions and models, but measuring that is a key component of understanding what we would have to do to deflect an asteroid coming towards Earth in the future. So here's a little timeline for the end of the mission, kind of the coming into the impact. So you can see this is fully autonomous coming in for impact. So about 30 days out, we start detecting the system. Coming down to 8 hours out is when the pre-terminal phase begins. And of course, we're coming in quite quickly. I think it said on an earlier slide, you know, at 6.6 kilometers per second or something like that nominally. So we're coming in very fast. So 60 minutes out, you can start to see dimorphos. You can see both objects. As we're coming in, they get bigger, of course, in the view. And 4 minutes out, we get our final divert maneuver corrections. Those should be done by 2 minutes out, and we should just be on a collision point there. And then we'll head in, and 20 seconds out, we'll get our pixel scale requirements for our final images from the main spacecraft. We'll be taking those images and transferring them up as fast as, you know, up to the last instant, and then Licia Cube will transfer whatever it sees. So CU has a lot of participation in this mission. It's not just myself. You heard from Alex Meyer earlier, the second point here. He's working on this mission on unrelated things like the research you just saw. He uses this tool Goobas, which Alex Davis, one of Professor Scheeres' former PhD students, wrote. And that's actually, there's an open source version of that if anyone's interested. Professor Hirabayashi, who's down at Auburn University, and Dr. Paul Sanchez, who's in SMED Aerospace, do a lot of work on modeling the system and the impact dynamics and trying to model what that beta factor is going to be. And I have a little different role. I was just selected as a participating scientist for the DART mission. So that's a little weird because, as I said earlier, this isn't really a science mission. It's a technology demonstration mission and really a planetary defense demonstration mission. But of course, we want to get what science we can. And so what my goal is personally as a participating scientist is to understand how the Bjorp theory or the Bjorp effect comes into play with the Didymos system. So as you heard from Kaya earlier, the Bjorp effect is this re-radiation of heat that can change the orbits over time. And it depends on the shape and the orbit and all these parameters. And so as we mess with the system by doing this kinetic impact, a lot of things will change, and we want to try and understand those things. Of course, we want to develop a new theory to predict what the changes will be and then measure those changes. And so just a few words about that. I'll show you a couple models here briefly, basically showing what Bjorp does and kind of what could happen. So this is a planar model. It's this is actually 1999 KW4 or mashup, but we have to model, of course, gravity. We just do the oblate spheroid primary plus J2 and the ellipsoidal secondary. We don't use the full Goobas because it's too slow for these long-term simulations we want to do. We have the Bjorp effect and solar radiation pressure. We have tidal dissipation. We model the librational motion of the secondary, of course, and we have third body tidal forces from the sun. And so I'm going to just skip that and go straight to the pretty plots. So you'll see several different results here. And the reason is because we don't have everything nailed down to predict everything clearly. So you see on the upper plots, there's two lines. There's the KW4 coefficients and the DP107 coefficients. And these are just binary York coefficients calculated from two different shapes of secondaries. We don't know what the shape of dimorphos is, so we don't know what the right coefficient is to model this. So clearly, if you have a bigger coefficient like the KW4 model, things evolve faster. You know, in this case, in 40,000 years or so, 35,000 years, the secondary would lose synchronous lock and be, you know, out at 13 kilometers or so separation. The eccentricity grows, and you see this is the libration angle, and so now it's circulating out here. If the coefficient's smaller, it would go slower and take much longer. The other interesting thing is the attitude and orbital motion is highly coupled. So depending on what initial eccentricity you start with, if you start with ranging from 0, 0.01, 0.02, 0.03, the dynamics actually change a lot. So there's this basically controls the free energy in the system. And so if you have even a very low eccentricity of 0.03, it allows for much higher libration angles, which can lead to this spin more rapidly. And so the evolution can get cut off earlier. So these are the types of models that we build and we'll investigate and see what will happen when an impact occurs somewhere in the middle of this. And the final thing with the impact is we'll change the shape. And so when the shape changes, the York coefficients depend on the shape. And so if we mess with the shape, this is just showing some forward models of if you mess with the shape, have a different shaped body, how does it change the coefficients? And so we'll be doing some of this modeling and trying to fit that based on the cratering and any subsequent shape change of the secondary. So lots to do, and it's a really exciting mission, and we're excited to be a part of it. So if there's any questions, please shoot them my way. I'll be happy to answer those. Thanks.
Thank you, Jay. Yeah, I'll refer questions to the chat. And Dan Luby is back. So he's willing to try again to present. So I hope, well, if you cannot stay, this is a little bit further than the schedule. There's gonna be a recording of the session that we can get to you. So yeah, you can go ahead.
Okay, thanks. Sorry about that again. I do not know what happened, but my computer did not like whatever happened. Okay, I don't know how much I got through before being disconnected last time, but thanks again for having me here. Basically, I'm Dan Luby from JPL, Spacecraft Navigator there. I'm going to go over some results we got from the JPL Independent Shape Modeling Team, which was part of the OSIRIS-REx mission. And so the content of this presentation is provided by me as a member of that team and the other members of that team, as well as some other members of the OSIRIS-REx mission at large. The focus of this is basically our team focused on generating a 3D shape model of Bennu using a method called stereophotoclinometry. We were basically doing an independent verification of the work from the altimetry working group, which was also part of the mission. And so stereophotoclinometry is basically the process of taking images, combining them together to stitch together 3D maplets across the surface, stitching them together to form a full 3D model of the shape, as well as other important ancillary products like taking those maplets, correlating them against the images to get 2D measurements of the optical data that you can push forward into OD so that you can use that optical information in your orbit determination. So it's important to note that OpNav, which is responsible for running SPC, and that was the major project that we were interested in, the shape model. But OpNav and OD are somewhat independent but really intertwined processes. So the outputs from SPC, it's important to validate them in the full context of OD to ensure that they're accurate. So this is what this work is about, that validation, and specifically focusing on how LiDAR data can help with that validation. So jumping right into it, we first started with just optical and radiometric analysis. And to do this, we did various filter variations. And essentially what we were doing is taking the SPC products, those landmark measurements I was saying, as well as the landmark estimates that come from SPC, putting them in the filter and then varying how we model them. In one instance, we give very few degrees of freedom, just bulk parameters. So essentially, think of all the landmarks, they can move together, like the center of them can move, so they all move together, or they can inflate or deflate, but that's it. The second case is where each individual landmark is estimated by itself in 3 dimensions, so each can move independently. And then the third case is we have those bulk parameters, but also each landmark can kind of move on top of that to some degree. So in initial fits, we find that the residuals behave pretty much as expected in terms of optical sample line residuals. Not really any strong deterministic signals in the data. The residuals are about on order of what we would expect given the camera parameters. So that's an initial validation that the optical data, when you put it into this OD framework with the radiometric data, with the dynamic modeling and all other modeling, things are consistent. Jumping in and looking at the landmarks, essentially what we want to do is validate that SPC is a converged process, that when we put it into OD, it's not changing the way the shape looks by adjusting the landmarks too much, that any adjustments to the landmarks are essentially not statistically significant. That lets us know that we've converged on a good result. So if we look at the updates to individual landmarks, what we find is in the case where we don't estimate bulk updates, we find that we had about 50-ish centimeter updates to the landmarks across the body. But when we do estimate both individual landmark updates and the bulk values, that decreases significantly down to like the 5 to 10-ish centimeter level. And it's important to note that the landmarks in this situation that come out of SPC are uncertain on the order of 5 to 10 centimeters. So these updates aren't really statistically significant. So the big difference between these two plots here is that the bulk parameters in the third case are absorbing most of the updates to the landmarks. So the actual shape is not changing, it's just moving in space. And in this instance, what we're estimating is a center of figure offset. And the reason this doesn't indicate anything bad with the SPC products is because SPC really isn't sensitive to this type of motion. It focuses more on relative geometry. So a type of shift like this OD is responsible for sensing it and removing it. So at the end of the day, this really shows that at least in an optical and radiometric context, these SPC products are consistent with the whole OD framework. Jumping forward into LiDAR, the reason we really wanted to use LiDAR here is because it's really sensitive to asteroid topography, and at the same time, more importantly, it is completely independent. So given its nice sensitivity and its independence, it's not used in baseline OD solutions, it's not used in the SPC process. So essentially we have this new data type that is completely independent of any of the shape modeling process. So if it's consistent with our shape model, then it's a good indication that the shape model itself is valid. So what we did is some pass-through analysis. So essentially we take a converged filter solution using just optical and radio data, and then compute with the residuals of the LiDAR with respect to that using data from OSIRIS-REx's laser altimeter, or OLA short. And we see up here that in general, we get data spread in the neighborhood of 1 to 2 meters in terms of residuals of the LiDAR measurements, though there are some strong outliers, but those outliers are generally associated just with viewing geometry. They occur with large off-nadir angles. So essentially, the more off-nadir you get, the more you're sensing the limb of the object, and the more that attitude errors and things like that can cause large range errors. So essentially what we found from this is, in general, the LiDAR data agrees well with the shape model without even having to fit it. And when it doesn't agree, it's really due to poor viewing geometry. So that leads us into, all right, we did a pass-through analysis, and signs seem to indicate that the shape model is consistent with the LiDAR data. What if we actually fit the data? Does that still tell the same story? So what we do here is, again, some filter variations based on that case 1A earlier. So for landmarks, we're just estimating bulk parameters. But for the shape, what we're doing is adding OLA biasing to the system in various different ways, shape bulk parameters. So the same thing of, do we move the shape as a whole? Do we inflate or deflate it? So those types of parameters. So the first thing we find here is that if you don't add any parameters to the system but do fit LiDAR, you do get a significantly degraded performance. You can see in the residuals here, some strong signals start to creep in, and that's indicative that when you do add LiDAR to the system, you do have to account for it in some way with some extra parameters. However, if we add just a few parameters, just those shape bulk parameters, so just again, center, figure offset, or an inflation deflation coefficient, we find that we get pretty much tracking as we did without the LiDAR data, reduced uncertainties, but our OpNav residuals aren't harmed by the inclusion of LiDAR, which really reinforces that shape model we have here is consistent with both optical, radiometric, and LiDAR data all at the same time. They're really telling the same story. It's also important to note that the shape bulk parameters we estimate come out to be very similar to the landmark bulk parameters. They're independent, but they both estimate a center figure offset of about 30 to 50 centimeters along the pole of the body. So again, they're telling the same story, which is important. As far as LiDAR data, we're fitting it in the 1 to 2 meter range. And again, where we get outliers, the outliers generally make sense with poor viewing geometry. So with that, I just want to conclude by saying this type of work, what we did here is take SPC products and validate them in an OD framework. And what we found is that they're consistent with radiometric optical data fits, the whole dynamic modeling and other models within the OD framework. It's consistent with LiDAR data in both a pass-through analysis and a full fit. In general, the optical and LiDAR data are telling the same story about the shape, that it is valid, and that if there's any update, the only update is really a center figure adjustment. So it really indicates that this is a converged shape model that doesn't get morphed in an OD framework. Also, beyond that, with all the filter variations that we looked at, the trajectories that we estimated are all pretty consistent with one another. They differ on the order of about ½ a meter, which, given the information content we have here, is not very statistically significant. So really all this data is leading to approximately the same orbit at the end of the day. So that would indicate that the shape model at the core of it is valid. So with that, this investigation really shows how LiDAR data can be effective in this kind of shape modeling, but in general, just usage in future small body missions is great for robustness checks, but also just the information content of it overall. So with that, again, thanks for the invite, and I'm happy to take any questions in the chat if you have them.
Sure. Thank you. That concludes the last presentation. And yeah, we'll just end up in a minute, give time for the discussion to happen in the chat. And yeah, so thank you everyone for showing up, and hope this was as interesting to everyone as it was to me. And yeah, I just wanted to conclude by saying that the activities of Asteroid Day continue. And you can see, well, on this link, asteroidday.org, all the events that are going on. And we're going to register this event there to make accessible the recording. Probably also on the Orca Lab Twitter handle or mine, and also on the email lists from which you got the information to this talk. And if you did not get an email about this and you still want more information, you can email me to be added to the distribution of that. And I'll just encourage everyone to keep on following the presentations. I believe that on this website here, there's like a Twitch stream of 5 hours, still going on for another hour now. And you can see on Twitter, hashtag Asteroid Day Live, or hashtag Planetary Defense, a lot of topics about this. And just wanted to end by saying happy Asteroid Day to everyone. And thank you.
Big thanks to Oscar again for hosting and organizing, just reflecting what's going on in the chat.
Yeah, thanks to everyone for coming. Maybe we'll do this every year, maybe live.
Hopefully, yeah.